Hello, everybody, and welcome to Lambda Lounge. We're back again after our brief summer hiatus. So, hello to everybody. So this month we've got a talk from Domas, who's going to give us an introduction to FS2, which is a Scala library that helps you out with your streaming problems. So do you want to introduce yourself, Domas?
Sure thing. So, hello everybody. My name is Thomas. I conveniently have a slide that talks about me. I don't have a lot to say, but I guess professionally, what would be worthwhile to say that I started as a Java programmer. And I've done a Haskell course in university, and so I've been always very interested in functional programming. So I had an opportunity at some point to jump into Scala, and that reminded me of the good times I had with Haskell, and I jumped on that opportunity, and I've been writing in Scala ever since, which is the last 4 or 5 years or something like that. And currently I work at the company. Yeah, so that's my introduction. Shall I jump into the rest?
Sure, I'll remove myself and Akeem from the stream, so it's all up to you. So we'll come back in if you need this stuff. So yeah.
Awesome. Thank you very much.
Yep.
Right. So with that out of the way, let's talk about the thing that you all came here to see me talk about, which is FS2. FS2 stands for Functional Streams for Scala. It's a library that provides a pull-based streaming abstraction that is effectful, resource safe, and concurrent, which are all amazing buzzwords, of course, but so maybe let's instead talk about what those mean in this context. So the structure of this talk will be such that I will first give some basics for that will lay the foundation for us to be able to explore the features of FS2 first. Then we will indeed proceed to talk about those features. And once we've discovered like at least a few of these features that I'm going to feature today, we'll talk about sort of the big picture and how all of these different pieces fit together to deliver real value to you as a developer. And at the end, I also wanted to mention a few things about sort of the wider ecosystem that kind of sprung up around FS2 and related libraries. So let's begin with the basics, or rather, let's begin with the setup. So one thing is all code on this talk. It has been compiled with mdoc. So everything you see is guaranteed to compile if you took it all and pasted it into your project right now. And as you can see here, mdoc provides these helpful comments for what a certain expression of code has evaluated to. So here we see the name X of type string has been bound to the string X. And I have a few other definitions to show what different things look like. Standard output also gets printed into into the scope block, which is very handy, and I'll be using that a lot in this talk. And one last thing to mention is that code from one code block carries over into the next one. So you see, I define X and Y here, but I use them in this next code block. And this is also something that I'll be using a lot. I'll be defining things in one slide and then carrying them over into the next one. To use FS2 in your project, first, you need to declare FS2 as a dependency. So I'll be using the core submodule as well as the IO submodule of FS2. So these are in the core FS2 project. And I'll be using the JVM versions. Both these submodules actually compile to Scala.js as well. So if you happen to be working in Scala.js, you can use both of those, with IO being recently added to the Scala.js repertoire. Once these are imported, what we need is to actually import the symbols into our code. So we're on Scala 3 for this talk. So I'll be using the star and given syntax instead of the underscore. And what we're importing is, of course, all the FS2 symbols. As an effect type, I'll be using cat's effect. FS2 is polymorphic in its effect type, so you can bring in your favorite effect, maybe Monix task or something, and that will work as well. I'm also importing cat syntax extensions to make some of the code a little bit smaller, which is useful for a presentation. And finally, because this is a presentation and I need to actually run code to show you things happening, I also have the unsafe runtime imported globally. This is not something you would do in a real project, but we need it here. So let's talk about the basics. I will cover effects, the basic stream type, as well as the basic combinators. So effects aren't exactly an FS2 thing. They are a wider thing that you will encounter when you write functional code, and not necessarily in every functional programming language. So I'll give you a quick overview of what effects are. Effects are a topic in and of themselves, so I certainly don't expect to explore them to any to a particular level of depth. So an effect looks something like this. We have f of a in here, where our effect, where f denotes our effect, and it sort of quote unquote wraps a value of type A. And this wraps carries a lot of weight here, and people who've done functional programming for a long time might squint at me for this, because this looks a lot like the box analogy for monads, and people don't like it. But I have to use a word, and that's what I chose. So let's take a look at one of the effects, which is option. So one way I like to think about effects is that what they do is they make knowledge that may be implicit in, for example, an imperative language, and it expresses it in your return type. So then an option is an effect that denotes that your value of type A may or may not be present. So if we, for example, look at this parsing function, an imperative language for functions which are only defined for part of the input, you may return a special value, or you may return null. And so you don't really see, just looking at the signature, that this function may not return the result. With option, we introduce that as an explicit acknowledgement in our signature. So in sort of our more functional method signature, we have the return type of option in. So that explicitly signals that we may or may not be able to produce a value for a given string. Another slightly less conventional way to think of effects is lists as non-deterministic computations. So for example, similarly, sometimes for functions like square root, you might implicitly make a decision that I will only return one of the possible values. But you can say that actually I will say that the effect of this function is that its output is non-deterministic. It may be 2, or it may be -2 if you're looking at the square root of 4, right? But really, those two are just examples. The meat and potatoes of this talk will be using the effect called IO. So IO of A is an effect that I like to call an action. What this means is, if I have an IO of A, that IO can be executed such that either a value of type A will be returned once that action is finished, the computation will fail, or the computation will just never terminate. And this similarly makes sort of this implicit knowledge explicit to us. So in an imperative language, you would simply execute a piece of code, whereas in this type of functional encoding anyway, you would instead return an IO of unit to represent an action that can be executed to perform this print line. So where in the imperative example, we simply print the hello, in our IO example, you see we get no printing occurring here. Instead, we get this IO of unit. And now we can execute this IO of unit to actually print hello. And we'll take a look at that in a couple of slides. IO of unit is a bit of a strange type because a value of unit does not mean anything. It's not really a thing. So let's take a look at something more meaningful. For example, IO of instant, representing the current time. So in this case, every time you execute this action, you will get the current time. Similarly here, we can pretend that this is a real API call, and you would get an action such that when this action is executed, you get the result from your API. And in both those cases, you can see we get an IO of instant here, an IO of list of strings here. We don't actually get the result. So those of you who are less familiar with an IO monad might be wondering, so how do you actually use these things? And what you do is you compose many of these actions. So you kind of say, okay, after you compute the current time, take a look at its value. And here we check if that value is after 2011, which it certainly would be if we were running this code today. And if it is, then follow this action of current time with this next action, API call. Similarly, once API call gives a result, we inspect that result and we print it into standard output. Otherwise, if we somehow time traveled into the past, just print this. And so this is what you do to construct your whole program when you work with this kind of an IO monad. You take these smaller actions and you compose them into bigger and bigger actions until you end up with a single action representing your whole program, and you execute that and things happen and you get your result. In our talk, we'll need to, of course, execute these effects, so we can actually explore what some of the effects that we created, what do they do when we execute them. So normally you wouldn't really be running this and safe run sync, but we have to in our talk to see some results. So if we print line hello, so this put function we defined earlier, it will just print the given string into the standard output. And you see, if we run it, we get hello. If we run current time, we get the current time. If we run the API call, we get that list that we defined to be our pretend API call. And if we run the big action, then all of those actions that we composed are executed at this time, and we get our final result here. So having explored the effects a little bit, let's now talk about the actual stream type that comes from FS2. So the stream type comprises of two parts. It has the type F here and the type A here. So what this type represents is a computation such that when that computation is run, some number of values of type A will be produced during this computation. And in the process, we will be evaluating effects of type F. And we'll explore what this looks like in practice. So first of all, let's look at pure streams. So with pure streams, you can see we have a stream that will emit some number of strings, and its effect type is pure. So this is basically saying it will not, in fact, be executing any effects. And we are constructing it just like that. We are saying that this is a stream which will emit these three values, a lot like a list or a different type of collection would. We can take a look at some other ways to construct pure streams. We can call .emit to create a stream of just one value. We can create streams from existing collections like we do here. We create a stream from this existing list. And we can also create just an empty stream. Now, because streams are computations and not actual concrete collections, that also means that we can have an infinite tree. If you come from Haskell, this is probably no magic to you, but if you come from an eagerly evaluated language, this is kind of neat, being able to construct infinite types. So here we have a string hello that gets up, and to it we append itself. So then we have another hello and another hello and so on. Let's try to run these streams. So as I said, they are computations. So to actually get the result out of these streams, you need to run it. So on pure streams, all you need to do is call toList, and it will run this computation and collect the output of it into a list, as it did here. We can also call things like toVector, and there's a bunch of other different ways to execute streams. You can call last option, and last is the same thing, so never mind that. And we can also execute this infinite stream. Now, I don't want to blow my stack, or maybe not my stack. I don't want to be stuck infinitely evaluating this infinite stream. So instead I say, give me just the first 10 things in the stream. And then we get a list that indeed contains 10 hellos. And we did not find ourselves in an infinite loop. Everything's okay. Let's take a look at effectful streams next. So effectful streams are created with a couple of different methods that exist on stream. One of them is eval, which takes an effect and creates a stream such that it will emit a single value, which is the result of that effect, and its effect type is determined by that effect as well. So current time, if you recall, it was an IO of instant. So now we have a stream of IO of instant. So it's a computation that will evaluate IO effects and produce instants. This time we know, in this case, we know that this is going to be a singleton stream, but in general, you don't necessarily know that information. You also have this repeat eval action, which will take your IO, and it will just repeatedly evaluate that IO to produce instant values. So this is a lot like the infinite stream that we saw earlier, except in order to produce values, it will not simply take that string that we sort of hard-coded, I guess, into our definition, but instead it will evaluate that action every time. However, because it has to execute these actions, we can't get the results of the stream quite the same way we did before. What you have to do is you have to compile these streams. So what compiling does is it will take this effectful stream, and as I said, will, for example, repeat eval, it will have to keep evaluating that current time effect. What it will do with compile, it will take the stream and will combine it into one big action, one big IO that you can then execute to get your result. So this is the same thing that we saw when we were talking about effects, how you compose smaller effects into bigger effects, except here the stream kind of does it for you. It composes everything that you described about your stream into one big effect. And here, and so you get an IO of option of instant here, because we take the last value and a stream could also be empty. So that means that we see an option here, but otherwise we see what we expected, that it is an action that may produce that instant. And here we see the similar thing, except with our infinite stream. So because once again it's infinite, I don't want to get stuck in an infinite loop. So I say, give me only the first 10 elements of the stream. We compile it into one big action. And this time we call toList. Again, like with pure streams, there's different ways in which you can get the result of the stream. But this time we say toList. And what we get is an IO such that it will evaluate current time 10 times, collect all the results into one big list and pass that down to me. And we can look at what this looks like. We can actually execute these. So if we take our current time once compiled, we will get just a single instant. Whereas if we take our infinites compiled, we'll get 10 of them. And you can see the timestamp actually changes a little bit. Albeit we have everything happens pretty much in the same moment, so it doesn't change much. But you can see that indeed it does, in fact, keep evaluating that action every time. So now that we talked about how to construct streams, let's talk about the combinators on streams and what you can do with them. So we've seen a couple already. We've seen take, which will just take some number of elements from the top of the stream. And we've also seen appending. Both are quite simple combinators. And notice hello world stream and current time once. One of them is a pure stream and the other one is effectful. And if we can use the combinators regardless of the effect type, which is quite nice. Some other things that we have are things like that you would expect on a collection. So map and filter are a couple. Map we can use to transform the things that come out of our stream using a function. So in this case, we just take the instant that comes out, convert it into a string. Once we run it, you see we get a list of strings, in which case, and in our case, it's a list of one thing, where that is a string. And we have filter. In this case, we just say, give me all the words that don't start with a W. So we just get hello and exclamation mark. We don't get the world. Some other combinators, flatmap. Is stream forms a monad, which means you can use flatmap. This is the monadic bind if you come from Haskell. So what that means is for every element in the stream, we can construct a new stream such that this stream will be executed for the first element, then for the second element, this stream will be executed for that element, and so on and so forth. So in this case, for every element, I create a new stream that emits that element twice. And so we effectively get a stream that just repeats the same element. Oftentimes, we also want to evaluate effects based on a stream. So in this case, we have our pure hello world stream, and we convert it into an effectful stream by starting to evaluate effects in the middle. So here, we take every word in our hello world, and we evaluate this put function, which prints the elements into standard output. And so when we execute it, you can see those elements coming out here. A vowelmap is another operator that is quite useful. It is basically flatmap with stream eval. So these two definitions here are actually identical. So with a vowelmap, whatever you return from this function will be wrapped into stream eval, and that will be flatmap. So this is just sort of shorthand, because this kind of a thing you just need to do a lot. A couple of combinators that we'll be using in other parts of the talk, and I wanted to mention, are fold and scan. So scan is a combinator that accumulates values from a stream using this accumulation function. So in this case, we take our hello world stream, we start with an empty string, and every time we get a new value from our hello world stream, we append it to our accumulator. So we get longer and longer strings with every new value appended. And scan will emit every result of, it will emit a new value every time this accumulation function runs. So every time you accumulate the next value, the total accumulation at that point is emitted. So here we get empty string, then we get hello world exclamation mark. Fold is like scan, except what you only get the last value. So it behaves the exact same way, but the stream will not emit anything until this upstream has terminated. So fold will keep accumulating until hello world has nothing else to emit. And at that point, it will say, okay, this is the value that we accumulated. So those sort of basics out of the way. I hope this gives us enough groundwork to talk about the interesting parts about FS2. So let's talk about all these in turn. So first, let's talk about effectfulness. This is in fact something we've already seen with pure streams and effectful streams. Streams are abstracted away from your effect. They are polymorphic. So we can have a stream of IO, we can have a pure stream, we can also have a stream of just some unrelated effect type as well. Here we have a stream of either. This is a perfectly valid thing to do. Having said that, IO will be most useful for us, so we'll be sticking to that. The next thing we will talk about is the resource safety that FS2 provides. So streams have this bracket combinator. that we see right here. And what this bracket combinator does is it requires you to provide two things. Number one is an action for acquiring something. So, this would typically be some resource like an HTTP client or a database client or something like that. And it also requires you to provide a second thing, which is an action of how to close that resource. So here we have a pretend resource, which is a random value. So we get a random value generator, generate a value incremented by 1 because I didn't want zeros in there. So I wanted values from 1 to this upper bound. And we use flatmap, which allows us to print this value, but the original value gets omitted. So what happens here in effect is we get a random value and we print into the standard output that we acquired this random value. Then our second action is, given the value acquired by our acquisition function, we need to provide a way to release that value. So this would be something like calling close on an input stream or something like that. In our case, we just printed to standard output again to say that we are releasing this resource. This is just so that we could play around and see how this works. So let's indeed do that. So we have a random number resource over here. And what we do is, once it's acquired, we take that resource and we simply print line. And then we compile the stream. We ignore its eventual outputs. And this is what happens. You see, we acquire the resource, then some work happens, and then the resource is released. All done by FS2 for us. So this part is maybe less interesting, but what is interesting is, well, actually, before I go into the interesting parts, naturally, when errors occur, things still get released. So in this case, what we do is we raise an error, and you can see we still have the acquisition, we still have the release. So FS2 will make sure that regardless of what happens in your stream, your resources are always released. You don't have leaking file handles or anything like that. And the interesting thing is that this composes, right? So you can do quite a number of interesting things with that. So let's take a look at this. We generate a random number, or rather we acquire a random number resource. And then for that random number resource, we repeat this hello world stream. And we repeating just repeats that stream infinitely. So we have hello world exclamation mark. So after repeating, the stream will be hello world exclamation mark, hello world exclamation mark, hello world exclamation mark, and so on. And then we take this random number of values of the top. Right, so you can see in this downstream part, we don't really have to know anything about any resourceness that happens upstream. All of it occurs behind the scenes. And you can see if we execute this, and here we just print every value of our stream into standard output. Here we acquired random value 6. We did some work with that random value 6, and then it gets released. And this was quite a simple example of composition. So let's take a look at something more complicated. So let's take the stream that we just constructed in the previous slide. So a stream that will keep emitting hello world exclamation mark repeatedly some random number of times. And for every output of the stream, we'll acquire another random number resource, this time up to the number 5. And for that number, we will emit that original string this random number of times. So we'll basically, for every string in our original stream, we'll repeat that string some random number of times, except our random number is a resource that needs to be acquired. And if we run this stream, you can see an interesting thing, or at least it's interesting to me. So we acquire the outer resource. This is how many strings there will be in total. And then for every inner computation, you see we acquire a resource, print hello, hello, and then we release it. We acquire the next resource, print world, world, and then we release it, and so on and so forth. So the interesting thing here is that the resource is acquired and released to cover sort of the minimum region of the code that actually needs this resource. This is very handy because once again, we did all this without having to know anything about how resources are required upstream. FS2 just manages all of this for us. One quick note is that typically you're not actually going to be using the stream bracket combinator manually. Libraries will most often provide you with a cat effect resource. And this resource, it behaves the exact same way as the stream bracket thing that we saw just now, where you have an acquisition action and a closure action. And the cast effect resource will performs the same function where it makes sure that if a resource gets acquired, that resource gets released. And so typically you would get a cast effect resource and you can lift that into a stream instead of using the bracket function directly. This is something that is more often the case than using the bracket function. So here you see we're doing basically the same thing that we saw a few slides ago with bracket, where we create, do some work, and destroy. So now that we talked about resource safety a little bit, let's talk about concurrency features that FS2 provides out of the box, of which there are many. So in this example, we have this function which pretends that it's doing a very heavy computation, which is calculating the length of the string. And you see it prints that, oh, we're calculating the length. It will sleep the number of seconds equal to the length of the string, and basically do that one more time. My apologies, my headset seems to have died.
No, you're okay. We can hear you now again. All good.
Okay, awesome. So we have an expensive calculation which we initiate from the string, which in practice will sleep twice the length of the string in seconds, and then a bit the length of that string. So this is just a setup for our parallelism test. And this is the interesting part here. So we take our hello world stream, which is hello world exclamation mark. We call this covary thing. So this is a little thing that sometimes is necessary to nudge the Scala compiler in the right way to say that we had a pure stream, but now we want to do effects on it. FS2 does an amazing job of not requiring you to do this. So most of the time you won't see it, but sometimes you need. Anyway, and the interesting part is here, par a vowelmap. So we already saw a vowelmap which takes a value and executes some action that is computed from that value. So by just doing par, what we do is we execute those actions in parallel. And here with this number, we can limit the number of parallelisms. So we can, for example, we can do any number, and FS2 will make sure that it will not be running too many things in parallel. And here we can see what happens. So we start calculating the length of all three of these things at the same time. But because we set up our sleep to be the length of the string, the exclamation mark you can see is done first, then hello and world follow shortly. But again, one interesting thing to note here is that the elements are still emitted in the original order. So we got hello world stream, right? So the lengths of these strings are 5, 5, and 1. And even though exclamation mark calculated its length first, you can see it's still the third one in the list. So FS2 just preserves the ordering for us. Except it doesn't have to. If you don't want to preserve ordering for whatever reason, you can call this other combinator, which is the exact same thing except unordered. And now, in this case, you can see the output is in fact all the same, except our 1 is in front. Because I mean, oftentimes you don't, in fact, care about the order of things. You just want to see things happen. We also have some other combinators as well that are very useful. So before we look at this, the partial and unbounded, I have a couple of helper functions here. So we have a function, which is an action that just sleeps a random amount, anywhere between 1 and 1,000 milliseconds. Then we have this hello world stream, which is the string stream, which is, I believe, just, I shouldn't have changed this just before I ran this talk. So this string stream, I believe it's just hello world exclamation mark as well, except it's repeated. And all we do is that for every element, we first sleep before we emit that. And then we repeat it infinitely. And so what we do in our actual example, so we construct a stream with two of these streams. So we have these other streams that we computed earlier. And all we do is we call this par join and bounded. And what it will do is it will run all of these inner streams in parallel. So string stream is actually the stream that emitted a random number of hello world elements, with the random number being a resource. And you can see we know nothing about that resource here, and that the resource acquisition and release is respected here. And all of this happens while running in parallel non-deterministically. So you see we get hello world, hello, hello, and so on. So you can see the outputs are just interleaved. And this was, all we needed to do to achieve this was call par join and bounded. Additionally, when you have concurrency, sometimes you need to do things based on time. So one incredibly easy thing to do, but that's incredibly useful, is interrupting, right? So sometimes you just don't want your actions to take too long. So in FS2, this is as simple as just calling interrupt after. And so you can see here we have an infinite stream. I don't know if you remember this from sort of the beginning-ish from the talk, but this is an infinite stream that just evaluates the word hello over and over. And what we do is we count how many values we see, and at the end we say just interrupt after 1 second. And so what we get when we compile this is how many times this has occurred in that 1 second. You can also throttle things. So if you are not comfortable with things happening infinitely, you can also call metered. And what this will do is it will throttle the upstream to, in this case, only emit every 10 milliseconds, right? And so what will happen is, as expected, when we count up the number of times that this stream has emitted elements through this metered call, we see that we get 99, which is about expected in a second. And all we needed to do was this metered call, which is very handy. Let's talk about what the pull-based section of the FS2 stream means. So the way I think about it, it's like sort of tugging on a rope. So if you are sort of at the end here, let's say you are this toList call, the way FS2 works is that it asks upstream for elements, and then upstream figures out whether it has some elements to give or not. So let me give you an example. We'll just talk through this particular instance here. So toList, right? What it wants is it wants to collect everything that comes from upstream. So toList sort of tugs on take and says, hey, take, do you have more elements for me? And take looks at its list of elements that it's emitted and goes like, well, I emitted 0 so far. So a vowelmap, can you give me the next element? A vowelmap says, well, I will if this gives me the next element, and then I can execute this function. This is an infinite stream, so indeed it has the next element for us to look at. We get that next element, evaluate this function, take its result, pass it down to take. Take takes note that, oh, I emitted one value, crosses that one out, and throws it at toList. toList, in its turn, throws it into a bucket and says, hey, take. And it tugs on take again and says, can I have another element? Take says, okay, I emitted 1, which means I can still emit 1. And the same process repeats. So a vowelmap says, infinite stream, can I have an element? Infinite stream produces an element. Function is evaluated. Take gets that value, crosses it out again, and then returns it to toList. toList once again throws it into its bucket and says, hey, take, can I have another element? And take says, well, I already emitted 2, so sorry, stream is terminated. Which means that it cuts off any evaluations of this upstream just by the virtue of this model. right? So this function will never get evaluated again simply because nothing downstream asks for any more elements. And similarly for this infinite stream will not be asked to produce more elements, and hence it won't. And this is an incredibly useful thing for a great many reasons. For example, let's take a look at this example. So we will take our random number resource that we defined some time ago, and we'll repeat it. So we'll keep acquiring this resource. And in these two lines, what we do is we accumulate the total, and such that when a total is greater than 100, then we terminate. So you see we get 11, 37, so on and so forth. You can see those resources get acquired and released until eventually our condition is satisfied and we stop. And you can see our total is there. Eventually we end up with 110. And by the nature of this pull-based model, even though we said random number resource repeat, where repeat being repeat infinitely, we have not acquired any more resources than we actually need. And again, this has no special setup. It's just a consequence of the model in which FS2 is built. So now if we explored all of those, and that's not quite everything in FS2, let's talk about let's look at an example of how all of these things fit together to deliver some great things for you as a programmer who has to make things. So let's take as an example this problem. So our problem is that we have a CSV file. This CSV file has 3 items on every row. It has a URL and it has 2 numbers. The first number, well, before I jump into that, and what we need to do is we need to query that URL for data, except we don't need to do it, we can't do it more often than the rate limit suggests, which is the second number in the row, and we have to do it up to the number of times suggested by the third number. So with every URL, you get the number of requests you can make per second, and we get a maximum number of requests. We write the result of all these requests into a file. The order doesn't matter. All we want is the data from those URLs. And we finish until either too much time has passed or we just written all the data, right? Some of these requests I would say some of these requirements are certainly not trivial, or at least if someone came to me, the Java programmer, 6 years ago or whenever, and said, to do all of this, I would have said, okay, give me 12 years and I'll do it. But let's take a look at how we can do this in FS2 in quite reasonable fashion. So first of all, we need some imports. We'll be using the files capability that comes from the FS2 IO submodule. And we'll need this path import as well. Related to files, we will need to work with paths. We'll be using IO effects, so we prematurely define that we'll be using this files IO. And we also pretend that we have an HTTP client because using a real one was inflating this example a bit too much. So this HTTP client has one function, which is basically perform a GET request on this URL and just get me the bytes. Get me the bytes that are the entity of this of the response to this request. We also model our CSV entries as well to make things a bit more convenient. We have this file entry. We have one URL, which is just a string. In our case, obviously in real code, you probably wouldn't want it to be just a string. You would want it to be a dedicated URL type or something. And we have the other 2 ints that we discussed. So we have the number of requests we can make per second, as well as the maximum number of requests to make to this URL altogether. And then we have a small parser that parses a single line into our model. And we produce an option such that if we successfully parsed, then we have a file entry, all is good. If we didn't, then we get a none, which means that file line didn't conform to our requirements for some reason. So with that out of the way, let's start building the pieces to solve this problem. So we'll start by defining what it looks like to read a file. So given a file, we presume it will be given to us externally. We utilize the file capability in FS2. We call this read all, and what it gives us is a stream of bytes. Obviously, we know that this is text, so we say decode these bytes into UTF-8 text. Now, because FS2 reads data in chunks, we will not necessarily be getting lines out of this. We'll just be getting, like, let's say 3.5 lines, and then the next 3.5 lines. And we don't want that. We want just the individual lines. So we use this text.lines to process this and get just the lines of this file. Then for every line, we perform that parsing function that we looked at earlier. And in our case, what we do is if a line doesn't conform to our requirements, we just throw our hands up in the air and we let the program blow up. In a real program, you probably would want some fancier error handling than just throwing a bomb at your JVM, but this is what we'll do for this example. Next, let's model our API call. So we have an HTTP client. We presume it's probably going to come from some library. And we have basically everything that comes from our from the individual lines in our CSV file. We have the URL, we have the requests per second, and we have the maximum number of requests to make. So the first thing we do in our implementation of this API call is we define the rate limiting. And this is, again, one of the concurrency features that just ships with FS2, this fixed rate function. What it will do is it will effectively tick this duration. And this will, because of pull-basedness, it's going to respect the amount of time it might take for the downstream to do its processing. So what this means in practice is that we get one tick, then we do our HTTP client code, and let's say it takes, let's say we can do 2 requests per second. But let's say our processing takes 700 milliseconds, but we only count our rate limit based on when we fire off the request. That means after those 700 milliseconds, we can immediately do another request. And fixed rate does exactly that. If we took too long, quote unquote, to process the last element, it will just immediately emit the next value. So if our processing takes a long time, that's fine. We will, in fact, won't be sleeping needlessly in between elements, which is great. We also have take max requests to limit the total number of requests that we're going to be making. And then once we have defined our time constraints, for every tick, what we do is we invoke our HTTP client. And from our HTTP client, we get bytes. So once again, not once again, but we expect that we'll be getting strings out of this. So we decode those bytes into strings, and we convert them into lines. The next thing we have is writing output to file, a very simple function that uses some of the things that we kind of already saw. So we have our output stream. So this is what we expect to get once we start executing those API calls, right? We'll be getting a stream of strings where every string is output of this API. And we will be writing those lines into this file output that's provided to us. So we take our output stream, we encode it into UTF-8 strings, into bytes using UTF-8 charset. And then using files IO, again, built-in capability into FS2, we write all of those bytes in. And once those bytes are written, we don't really care what comes out. Now that we have all these different pieces, let's assemble the whole program. So we assume we'll be getting the file from which to read things, as well as the file to which we will be writing our eventual output from the caller. We'll be getting a timeout from the caller as well. And finally, we expect that we'll be getting an HTTP client from a caller as well. It's in a resource because when you are instantiating HTTP clients, there will typically be something like in initializing a connection pool or things like that that need to be set up and need to be torn down once they are complete. And let's take a look at what the assembly of these things, in addition to the steps that we outlined earlier, looks like. So we define a resource of our HTTP client. Then given our HTTP client, we read the file. For every line in the file, we perform this call API function. Then we part join with this little 8, and what this means is it will run 8 inner streams at a time. So let's say you have like, an extremely long file. Let's say it's 2 terabytes long, and apparently you want to call some API for every line of this file. That means we won't be overloading our memory with this file, right? We'll be just reading 8 lines, and then we'll be calling the API for every respective line. And only when one of them completes, we'll read the next line and the next and the next, which means that you don't have to hold a huge, massive file in your memory, which is great. Once we set all of this up, so we read from the file, for every line in the file, we call an API such that we run 8 of these in parallel. 8, by the way, is just arbitrarily decided by me in this case. We have this API out stream, which is a stream of strings, because what part join does is it will take the output of every inner stream and just non-deterministically interleave it as it gets data from these individual call API calls. And we will call write output. So write output takes our API out, takes our file out, and it will construct a stream such that that stream will just be writing into a file. And so what happens here is these streams that call the API get some data from an API, convert it into a string, and a string is immediately fed into the file, and then it can be garbage collected. So similarly to how with the file, we don't need to keep the whole file in memory. If we have an HTTP client that's capable of streaming the data, we also don't have to keep the data that comes from like our external APIs in memory as well. We can just get data piece by piece, throw it into the file, and discard it, or garbage collect it. We don't need to do any explicit discarding. Once all that is assembled, we have this one last piece, which is interrupt after. So we have our timeout as defined in here. And once that interruption happens, FS2 will make sure that in case we are not finished, it will release the HTTP client. It will make sure that all the API connections are terminated and all the file handles are closed, all for us. We don't need to think about that at all. And then we execute it, and we get ourselves an action. So let's think about everything that we just saw. So we had a problem that I would say was not quite trivial. And last I counted, our solution was 65 lines of code in total. When I say 65 lines, I included all the comments and all the white space, and I was pretty generous about breaking lines for parameter lists because this is a presentation that doesn't have a lot of width. So in order to be able, for you guys to be able to read it, I had to break lines generously. And in those 65 lines of code, we have lazy file and API reading, which I've already talked about, right? So we don't have to hold all of the data in memory. We just need, we only have as much data as we need to be doing the current thing. And as soon as the data is not required, it is garbage collected, and we get the next piece of data. We have safe resource usage. So in individual pieces, we never had to worry about resources, and yet we had this resource safety threaded to us by FS2 implicitly, which is also great. It makes it incredibly composable, and I think that's one of the great attraction points about FS2 as well. We had parallelism that was basically free. We had to call par join, and suddenly we're reading from multiple APIs at the same time. One thing to note is we deliberately set up our problem such that the order did not matter. I actually set it up because I just wanted to use par join. I thought it was a nice thing to showcase. But if the order did matter, we could still utilize things from FS2 to include some level of parallelism. For example, we could say that we do need to emit things in order, but we could still run the subsequent calls to the APIs and simply buffer that data into memory to some extent. Similarly, FS2 allows us to control these kinds of things. So the solution would have been a bit longer, but there's still nice things that we can obtain by using FS2 in that setting. We also were rate limiting calls to APIs, which is, I think, also not necessarily a trivial problem. Again, if I had to do this in Java, however many years ago, I don't know what Java looks like nowadays, I probably would not have been very happy about that. And finally, we have low-level access to bytes that come out of files and such. Typically, when you work with libraries that give you file access, or for example, things that ship with the JVM, you'll just be getting strings out, just because dealing with bytes is not something people want to do because it's quite tedious. But with FS2, because it's so quick, all we had to do is text UTF-8 the code, and we were having strings. It can actually expose us as a low-level API, and we don't really pay much of an ergonomic cost in doing so, which is a very nice property in my opinion anyway. Right. So let's talk about one last thing that I wanted to mention. So, and this part is going to be rather short because we're already nearing an hour. So first, things that are already built into FS2. So we already saw file I/O, for example, but FS2 also has network I/O, so low-level TCP, UDP, and TLS utilities, as well as standard in and standard out. And all of them are, well, just using them is a lot like what you saw me doing today. It's quite straightforward. And because of the straightforwardness, an ecosystem sprung up around FS2 that uses FS2's primitives, which are built from scratch, as opposed to using, for example, the JVM ecosystem. So, for example, you have Skunk, which is a library that allows PostgreSQL access that's built not on JDBC, which is quite interesting because, as I said, since recently, FS2 I/O also builds for Scala.js, specifically for node environment. And because Skunk was built on FS2's primitives, Skunk was also rather trivially ported into Scala.js. So now you can you can connect to your Postgres databases the same way as if you were on a JVM, if you were, for example, running an AWS Lambda, or if you were making an Electron application. For example, I personally have built an Electron application in Scala.js because, if you need a desktop application that is not going to have huge scope, you just need a small thing, and you're a Scala programmer, the options are not necessarily plentiful, but because we have Scala.js, we can utilize Electron, which is, all over the place, and it's very well developed. You also have things like Doobie, which is another great database access library. You have HTTP4S, an incredibly mature HTTP library, as well as just a myriad of other things, a couple of which that I've used personally, which is why I picked them. We have FS2 data, which is a lot of what we've seen before. So reading from files, but it gives you capability to read CSVs, read JSON files, read XML files, and it's also very, very useful. And similarly, Mongo for cats is another library that's much like Skunk and Doobie, allows you access to Mongo. And yeah, I reached the slide and I found myself not having much else to say other than FS2 is kind of nice, and I think everybody should at least give it a try. I think through its model, the pull-based model, you can achieve very, very composable programs that you can add together into big and sophisticated programs that have, things like parallelism and resource safety and all of that given to you for, as you saw, not a whole lot of cost at all. So yeah, give it a try and yell at me if you find that you don't like it, but I hope you don't. I hope you like it.
Yeah, thanks very much for that talk, Domas. That was really good. And no one would ever guess that you were, this is one of your first times giving a talk, because it was very professionally done. And also bang on time as well, so well done.
Yes, I've mentioned to you before the talk, but I've had a practice run, which I think I wasn't even finished, and I was at an hour and 5 minutes. So I'm very impressed with myself.
So maybe a question for myself while anyone else gets a chance to ask their question. So is there a way of getting FS2 to interact with other streaming type libraries on the JVM? I'm thinking, for example, like reactive streams stuff. Is there a way to make them play nicely?
So there is for reactive streams, there is in fact a cross-compatibility module in FS2 core. I haven't used it myself personally, but I know it exists. There is when it comes to some more streaming libraries, people in the Scala ecosystem, in the Scala community, would have probably come across a small thing called Akka. So there's a library called StreamZ, which allows you interop with Akka streaming as well. And well, that's the two I know off the top of my head, which probably covers the biggest interop use cases, but I'm sure there's more.
Mm-hmm. Yeah, that's cool. Yeah, I know HTTP for S. There's a version for Kotlin called HTTP for K. Amusingly, so I'm not sure if it uses FS2 internally or something different, but yeah, be interesting to find out. So yeah, if anyone's got any questions for Domas, then far away. I shall put them up on the screen. Oh no, yes, there you go. Here's a question. Question from Squirrel Boy, whoever that is. I'm not sure. I'm sure I know who that is, but anyway. What's next in your code base? Will you be moving more things to a functional style, and what are you most excited about using next?
So at Precog, where I work right now, we actually already have like a fully functional stack. It's all based on all the type level projects, so FS2, cat effect, and so on. So we can't really move more functional, I guess. But I have done some migration from more imperative style to more functional style at my old work. For example, I worked with Akka before, and I started introducing more functional elements, and that's certainly doable if it's something that you're thinking about yourself as well.
Cool. Yeah, thanks for the question. Any more? Who knows? It tends to be pretty random whether we got questions or not.
One thing I realized I actually somehow omitted is that I actually didn't even cover all the features of FS2. Unsurprisingly, probably. It's probably impossible to cover any library 100% in an hour. But there is a lot of other concurrency primitives. There's things like topic that allow a pub sub model and things like that. So there's a lot more to explore in FS2 as well, even if I didn't mention something that solves your problem.
Yeah, a question from Ali says, I've seen people use FS2 for control flow rather than just functional streams. Could you talk more about the feasibility of that?
So I think some of the stuff that we've seen was already kind of in that direction. So timing operators, so like fixed rate, like you could really think of them as more being control flow, right? We weren't, strictly speaking, computing anything at that time. We're just controlling how often things happen in that case. And you can do similar things with even simple operations like append. I've done that before with Ali, who is my acquaintance. Hello. We've done event streams to drive things like a user input. So for example, user clicks here, you get an event into FS2, and then it branches out into different streams depending on what the user clicked on and things like that, which is certainly something you can very much do. And also, I believe Fabio Labella, I hope I'm pronouncing his name right, has a talk on specifically control flow and FS2. So that's another thing you can check out if that's something of interest.
Yeah, it's good. It's always good to have a ringer in the audience to ask you questions, I find.
Yeah.
So another question, maybe this is the last one. Can you tell us more about what else uses Precog in the functional stack? So I guess you mentioned the top level type stuff. Is there anything else?
Great question. I think really Cat's effect is obviously a big one. Cat's effect and FS2 are really the core of writing probably anything in a type level stack. We use HTTP for res. We import a bunch of stuff from Chris Davenport's Davenverse projects. And yeah, just smaller libraries here and there. As I mentioned, our product is about getting data from like APIs and databases and just a variety of different sources, as well as writing to a variety of different destinations. So as you work with those different sources and destinations, you typically will, your first point will be looking for something that already does that job, right? And preferably that's compatible with your stack, in our case, type level. So we certainly have used various different type level libraries for all those different small jobs. I just can't remember any off the top of my head right now, unfortunately.
No, that's cool. Yeah, well, I guess let's maybe wrap it up there. But that was a really good talk, Domas. So thanks very much for giving us.
Thank you, Connor.
Just to say for anybody else who would like to give a talk, we're always looking for people to give a talk because basically it saves us having to do it. So if I don't get any volunteers, I'll have to do it next month probably. So please save them from do it. That would be really good. But also, if any questions, pop on Discord after the session. I think there should be a link in the Eventbrite description, I think. Yeah. So yeah, I think let's call it even. So yeah, thanks very much, and see you next month.
Thank you for having me, and bye-bye, everyone.
Cheers. Bye all.